Okay, so we're in the depths of getting into the depths of neural networks. It's meant to be a pun. So last time we left off, and we had just finished talking about radial basis function neural networks. So as a quick reminder, neural networks, RBF and N. So as a reminder, I initially pitched these as kind of a modification to the single layer perceptron, to the binary classifier, where we get to transform the space to allow us to separate, to classify things that were not linearly separable. And then I finished off saying that even though I kind of pitched it as sort of a modification of one neuron, really what we built was a network of neurons. And so the way that looked like is we had our feature set, you know, here, our x1, x2, all the way up through xn, and this was our feature vector. X vector, and then each one of those things fed in to a potentially different number of receptive field units. And so for the radial basis function, let's say I had R1, R2, all the way up to maybe an RM. And each one of these receptive field units took as inputs the whole X vector. And so all of the inputs went to all of the field units. And so, so that I could say like X1 goes to all of them, X2 goes to all of them, all the rest of them go to all of them as well. So we would say that these receptive field units are fully connected to all of the inputs. And then those receptive field units, so I can write these as receptive field units, and they are defined by a radial basis function which itself has a center, which I can call maybe CI, which is configurable. And so the idea here is you come up with a set of these, so these radial basis functions, we're saying they could be depressions in the feature space. And so they're maybe one everywhere, except for a particular small section of the feature space where they're depressed in less than one. Or they could be zero everywhere, except for as part of the feature space where they get raised up. Like so, it's kind of like they're sort of a bell-shaped curve or a bell-shaped depression in the feature space. Is one way to kind of view it here, and that allows them to promote or demote certain regions of the feature space, so that you can kind of, instead of being stuck with a line like you would be with a single neuron. It's like a single neuron basically says, I'm going to define a line, and everything above the line is in one class, everything below the line is another class, and we can kind of measure distance, you know, toward that line. Well, instead of defining it that way, now I can actually say there are distinguished regions of the feature space that I can add together and say these regions represent one class, these regions represent another class. And so if I want to do classification, this allows me to do much more powerful nonlinear classification, and by creating these sort of units here. But I have to decide what these centers are going to be, and that could be done with an optimization meta-heuristic, for example, or it could be, and that would just be one of the parameters that you would be optimizing. Another option is you could use from machine learning, and we'll talk about how we use neural networks for clustering, but some clustering method where you look at all of your data and you say, does it tend to be that that things from a particular class tend to cluster in some area of the feature space? And if they do, you could use the center of that cluster as one of these radial basis function centers. And so you could choose these centers in some particular way. But then once you've got those centers and everything, then the last thing you do is for the output, you bring them together into a summing junction. Where each one of these has a weight. And so I guess to sort of be similar to what I did before, I'll draw a little gain function here, where this is W1, this is W2, and this is WM, so that you get a weighted combination of those features so I'll call this thing here X bar, which is just the weighted combination of those features with, so this is the sum of Wi, Ri. And then I've got an activation function here, and this activation function could be, for example, if I'm doing classification, it could be a threshold, or if I'm doing function approximation, then maybe it's just linear. So it's just like the identity function that passes it straight through. And so saying this, actually, if you think about it here, these receptive field units really are themselves artificial neurons with a special activation function, which is the radial basis function. So these are really artificial neurons where all their weights are set equal to 1, but their activation function is chosen to be a radial basis function. So really, we've now networked a bunch of artificial neurons together. We have kind of our standard artificial neurons. So this is, here is just back here. We can call this sort of an output neuron. And then these here are just kind of these hidden neurons that, so we think of these as M neurons, units, that just happen to have unity weights for all of their inputs. So M neuron units fully connected to the X vector with unity weight and radial basis function activation. And then these, of course, are just the inputs. So a radial basis function is our first example of a network of artificial neurons together, a neural network. And so that's why we call this structure a radial basis function neural network, is it has a so-called input layer. So we call this the input layer. And it has a hidden layer. So I'm going to see if I can just slightly nudge this up. So I'm not going to change any of the text. I'm just going to shift everything up a little bit. So this shouldn't require any erasing or reconfiguration on your part, if I can manage to do it. I think I can do it. I think I can. All right, so then this here is what we might refer to as a hidden layer, also called latent variables. And then we have an output layer, which in this case is a single neuron. But if we were doing a classification task where we had more than 2 classes, then one way to do that would be to have multiple output neurons in parallel that don't talk to each other, but then weight these hidden neurons in different ways. So then that way, this like, if we put a threshold function here, then this would be a 1 or a 0 based on presence in one class. If we put another threshold function here, there'd be 1 or 0 due to the presence of another class. And you could have a so-called one-hot encoding where, let's say, at 10 classes, we could have 10 outputs where only one output was on at a time. And there's a bunch of other different ways you could do this here, but the idea here is you could have multiple classes or just multiple types of output. And it doesn't have to be classification. It also could be function approximation where they're all linear, but they're just weighted in different ways. And so if you want to predict, for example, you've got all of this past history data on a student, and you want to predict, are they going to graduate? What grades are they going to get? Are they going to go to med school? There's all these things you might want to predict. Well, it all comes from the same data, but you could have multiple output neurons doing different predictions. So this output neuron predicts what's the probability of them graduating. This one is what's the probability of them becoming a doctor, et cetera, et cetera. So we could have multiple inferences happening in that output layer. And this is the basic structure of most, especially these so-called feed-forward neural networks. An input layer, which is just the inputs, a hidden layer, which are these intermediate neurons, which we call latent variables because nobody sees their outputs. So our stakeholders who we give our predictions to, they don't know what's going on in here. They're just here so that we can collect them together to produce the true outputs. And so that's the output layer. And so when there's just one of these, this is called a single hidden layer neural network. When there is more than one, it's called a deep neural network. So a deep neural network is just a neural network with more than one hidden layer. Okay. So questions about this abstract. And again, this is all an abstraction. I see a question in the chat. This is all an abstraction. Like we call the inputs an input layer, but they're not, there's no neurons there. We just model it when we draw it out as like a layer of inputs that is upstream of these hidden units in the middle. But again, when all this is implemented, this is just going to be a vector, and each one of these are just going to be functions. And so like when you actually implement this in a computer, you're not building algorithmic structures that look like this. You're just building functions. And this just gives you a way to draw out the functional relationships between the variables. But in reality, how it's actually implemented is just, we know the function for this, it operates on the vector for this. All these functions outputs get summed together, that generates another variable. That variable is operated on by another function. So I could write all this out in math. And so as you move on doing more work with neural networks, then you find that this perspective isn't really used much. People might talk about how many hidden units they have or whatever, but when they're actually writing the theory of what's going on, they just a lot of times just use matrix algebra. They say, they simplify everything down into vector operations where vectors are operating on matrices are operating on vectors. Those vectors are then being operated on functions, and the outputs are then getting operated similarly. So it just is a string of functions and vector operations. Or tensor operations, it's kind of a generalization of that. So that's kind of what's going on here. That's our simple radial basis function neural network, which is our prototype neural network. So there's a question, can a hidden layer have a meaning in a physical systems like states in a state space model, or are they always arbitrary, defined by the provided data? Well, yeah, a hidden layer, it can have meaning, but hidden layers are not unique for a given input-output map. So if you take a course on systems theory, the latent variables often have a lot of flexibility in input-output maps, and that what I kind of mean by that is there can be transformations of these latent variables that can put them kind of in, you can sort of restructure them, and it requires you restructuring the weights of the output matrix, maybe restructuring the weights going into here. So in a general neural network, these would have, going from input to hidden layer, those weights would be adjusted too. And so it may be that you can reorganize the hidden layer and still get the exact same output. And so you don't want to, they don't necessarily have a physical the physical meaning, but the dimensionality sometimes is important. Like we know that in order for us to properly map this input to output mapping, we need at least 8 latent variables. And it's sort of like degrees of freedom. We need to be able to slice up the input in 8 different ways in order to put it back together to properly approximate the function we're looking for. So it's more like the dimensionality of the hidden layer is kind of the most important thing. Now, I should say, I guess I should back up a second and say, there are certainly models of natural processes, psychological processes, where these latent variables do have meaning. So if I'm trying to decide or describe statistically how someone makes a decision, then there are latent variables having to do with like their internal states, like how a person feels, their emotion at the time, how hungry they are. These things that may not be observable to me, but I need them in order for my theory to work. And that's really, in statistics, what we mean by latent variables, as these are variables that are not obvious from the data, but need to be inferred to exist in order for the input-output relationship that we observe to make any sense. So sometimes they'll have meaning. In general, though, if you have one latent variable description, there is some isomorphism to a different latent variable description that will give you the same input-output mapping, but maybe a more mathematically convenient way to write the latent variables. So I hope that answers your question. All right, any other questions about this? Or kind of intro to a simple neural network? Okay. So if I I see another question online. To what extent can the hidden layer be made explainable? Seems like it's kind of a black box. And yeah, so when you hear a lot of buzz about explainable artificial intelligence, about neural networks being black boxes, then it has to do with the fact that neural networks get their flexibility to approximate functions through a high degree, a high dimensionality of this space here. And because these transformations in the middle don't have physical interpretation, then they are prone to being difficult to explain. But these are the things that are kind of doing the heavy lifting of the neural network. There are ways in which you can add explainability. So a PhD student of mine who graduated recently was doing had a deep neural network that analyzed video data of social systems, and the neural network could predict phase transitions in the social systems over time. So, how far away from looking at a 30-second video segment, he could tell how far that society was to a particular transition where everyone was switched into one sort of behavioral pattern. But it was like a 21-day video total, but from 30 seconds, he could predict where things were in there. And so you'd have to say, well, what the heck was the neural network looking at? So he built one neural network that predicted, what probability, what was this from a 30-second video segment, where was kind of the likely position in the 21-day period that the average time it takes for the social transition to happen. And then after he built that neural network and showed that it was pretty accurate, he built a second neural network that could sort of, well, I don't want to say it exactly like that. He built a second tool that could look at the hidden variables and then interpret them back in the context of the video data that was being forced into this. And so what he was able to do is, as one neural network was running, he had another inference engine looking at the hidden variables, merging it with video data, and turning them into little spotlights on the part of the video that the neural network was looking at in order to make its decision. And so this second tool what allowed for someone to say, oh, look, it looks like these behaviors that it's highlighted are the important predictors of this transition. So it allowed them to sort of spotlight that. So, but my point is that these systems themselves become so complex that we have to actually build tools to analyze these systems if we want them to be explainable. The other things you can do is you can add symbolic meaning to some of these things so that they're not all just purely numerical, and you can kind of restrict the structures that can exist here so that they have meaning kind of by default. So they're not just sort of all fully connected. And that's kind of what we're going to get into when I talk a little bit about a convolutional neural networks here in a second. So it is a fair point that the flexibility in these neural networks comes with a lack of understanding of what's going on inside them. All right, so any other questions? I think that's all the ones online. Okay. All right, so I've been talking about function approximation. So, so that means that if you give me any function, and it could be a simulation. So I give input variables to simulation, I see what the output is. And I mentioned that radial basis functions are used in surrogate optimization, where you run an expensive optimization objective, and it takes a long time to calculate, but gradually you train this function approximation tool here, this radial basis function, to become a stand-in, a surrogate for the costly optimization objectives. So as this starts to become a good approximation of the real optimization objective, it can be calculated very quickly. And because it can be calculated very quickly, it's much easier to take optimization steps using the surrogate than it is using the real thing. So function approximation is an important, it's sort of, if you get rid of the activation function, that's really what everything's doing up until the very end of a neural network, is it's approximating a function. And then at the end of the approximation, you might threshold it or whatever to get some classes out or class membership out. So function approximation is really important. So then the question was, what sorts of functions can neural networks approximate? Are they limited? Are they constrained? Are there certain functions that are out of reach? And there have been a number of so-called universal approximation theorems. And there have been several of these, but I'm going to refer to just sort of a one that is attributed to George Cybenko, where it basically says, for all kind of well-behaved functions, so there are pathological functions it doesn't apply to, but pretty much any function we worry about as computer scientists or engineers, then a neural network, so I guess I could say virtually any function can be approximated by a neural network with a single hidden layer of sufficient width, so long as activation functions are non-polynomial. So that's kind of a compressed version of the theory. All this is basically saying is, so long as you don't have polynomial, like linear activation functions in the middle of your neural network, then, so as long as you've got that non-linear transformations in the middle of that neural network, every single function that you would want to approximate, there technically exists a neural network, and may have a huge number of hidden nodes, but there will exist a neural network with perhaps a large number of nodes where each node is going to have an activation function that'll be this kind of non-linear, non-polynomial activation function that will be able to approximate your function to arbitrarily small differences. So if you could have sort of an infinitely wide hidden layer, you could approximate anything. So this is the so-called Universal Approximation Theorem, or UAT. And so this shows us that neural networks have a lot of flexibility, a lot of power. But the problem with single hidden layers like this one here is, like I said, this could need to be very wide, and the functions that you might need to load into here, like these radial basis functions, are kind of complex and hard to optimize. Like you have to choose these centers, and if you have a bunch of these, then you got to choose a bunch of centers. So the Universal Approximation Theorem doesn't help us find that network. It just says that that network exists. So there have since been additional Universal Approximation Theorems that have focused on neural networks that have finite width hidden layers, but multiple hidden layers. And it turns out that although you may not get quite as much flexibility out of having multiple hidden layers of finite width, you get a whole lot of flexibility. And so generally, we prefer deeper hidden, I don't say we prefer, but there has been a preference for deep neural networks with layers that maybe are, I mean, they're still large, like there might be 256 units or 1,000 units. Like there'd still be a lot of units, but we're not necessarily just trying to make a single layer wider and wider and wider. We're now creating ones that are deeper. And so we have multiple hidden layers. And this can actually make the training process easier, and sometimes maybe adds to the interpretability. So the Universal Approximation Theory basically is saying a single layer is enough. So a single layer is enough, but no guidance on how to find it and how to build it. And no idea how large it needs to be. So instead, consider deep networks. And deep networks is when we have greater than one hidden layer. Yeah.
If we ensure the equally spaced in the domain, would that be a good strategy to say that those centers will approximate the function better?
Well, so there's a question of, at least for the case of radial basis function neural networks, could one strategy be just kind of pepper the space with pepper the feature space with equally spaced centers, kind of like a grid of centers with a kernel function sitting on top of them. And that is certainly one approach, but what you'd find is that you're probably going to need far more, you're going to use far more hidden nodes than you probably need, because most classification problems are what we say sparser. So you don't actually need access to the whole space, and so if most of those won't be used. And so you end up having, managing a lot more of those. And then you still have to make choices on, well, how close do they need to be? How many of them, et cetera. So that's the reason why a lot of times when people do this radial basis function, because they're looking for smaller numbers of units, they say, all right, given I only want 5 units, where's the best 5 centers I could place? And I'll place those there, and then I'll optimize the weights after I do that. Yeah. Any other questions about any of this before we move forward? Okay. All right, so enter into this the multi-layer perceptron. So this is a generalization of the single layer perceptron in a deep architecture. So the multi-layer perceptron we're going to see will end up giving us a lot of the same power for approximation as the radial basis function neural network, but it has much more control over actually ensuring that our optimization algorithms are going to converge on a good network. So we'll see how that works here. So multi-layer perceptron, and we'll see that there are some popular multi-layer perceptrons that are themselves inspired by aspects of the human brain. So this is otherwise known as an MLP. All right, so in a multi-layer perceptron, it's just going to be your input layer. So input layer. And then from there, we're going to connect it to a series of hidden artificial neurons, just your standard conventional ANN units or artificial neuron units. So these might use, you have control over their activation functions, but they're going to stick to some of the simple ones that I talked about before. Rectified linear units, linear activation functions. They're going to have sigmoidal activation functions, tan-H activation functions. So kind of the standard sort of switching-like or gain-like activation functions. And so we have everybody's connected to the first layer here. And then we've got additional hidden layers, which look exactly like the first hidden layer, Gesundheit, but they take inputs from the previous layer. There can be, well, I'll put, these layers do not have to have the same number of nodes. So we could have an n-dimensional input layer, n-dimensional input. We could then have, some m-dimensional layer 1, some, o-dimensional layer 2, some p-dimensional layer 3, and so on. And then the output dimension might, be just 1 or 2. So depending on what type of output we're having here. So each one of these layers can have different dimensions, and they're connected to each other. So there's, all sorts of connections that I'm just kind of like, summarizing this way. And in general, we view them, maybe I'll draw an output layer over here. And so we're going to, these are our hidden layers. And just as a reminder, it's deep if more than one. And this is our output layer. And so in the multi-layer perceptron, the perceptron usually means a classification problem. That said, generally when people use these feed-forward networks, a lot of times the term multi-layer perceptron just ends up becoming a synonym for a feed-forward neural network. So that's the other thing I guess I should say about these. This is a forward architecture. And all that I mean by that is that information flow goes from left to right. There is no, in theory, some of these latent variables could connect back to previous, to other nodes or to themselves. There could be recurrent connections, but in this case, it's all downstream. So it's just an input comes in, it gets processed by functions, they get processed by functions, get processed by functions, they get processed by output functions that produce outputs. So it is a feed-forward neural network. And so sometimes people use an MLP as just kind of a synonym for feed-forward neural network. But initially, MLP was a feed-forward neural network used for classification. And it is deep, it has more than one layer. Why do they care about calling it deep? Well, again, because the Universal Approximation Theorems suggested that you don't need more than one layer. So the deep neural network community, or the neural network community said, well, what if we add additional layers? What does that give us? And for one thing, it can help with training, but the other thing is it creates these kind of tools that have modularity. So you can actually build input processing neural networks that then get, that you bolt on additional neural networks later. So you end up getting an interpretation where you get kind of a filtering and an input processing early, and then actually like the computation going on later, and then the output. And so, you know, there are whole papers written, and we'll talk about this, about people just sort of giving you the input layers, sort of saying, you know, you've got a video and you have no idea what the features should be. We're going to extract features for you, and those features are going to work for any video you're going to want to work on. And so we will build the feature extraction neural network and train it for you in a bunch of videos. You can take that, pull it directly into your application. You can retrain it a little bit, tune the weights if you want, or you can leave it exactly as it is, and then treat the outputs of our neural network as the inputs to your neural network. And so that's what deep neural networks give you, is this ability to bolt on neural networks so that you can get these like Lego bricks that can be plugged in together. All right, so that's our generic MLP. And if you've, and remember these are, these here in the middle, these are our latent variables in the hidden layers. And the other kind of note that I'll mention here is generally, I'll put down here, activation functions are nonlinear. And that's because if you had a bunch of linear activation functions here, then the output from one hidden layer to the next hidden layer would just be a linear combination of the outputs from the previous hidden layer. But if that hidden layer was a linear combination of outputs from it, then you do a little bit of algebra and you can end up generating connections directly from one layer to the far layer, skipping this layer here just by changing the weights. So in other words, if all of these things are linear, then you can replace a bunch of hidden layers by a single hidden layer with weights that kind of accumulate all the weights from the previous one. So it doesn't make any sense to have a bunch of linear activation functions in your hidden layers, because those hidden layers are just doing extra work. They're just sort of multiplying something by 6 and then dividing it by 3. And like, if you're just scaling things up and down and up and down and up and down, just put all that stuff together and figure out what the one factor is. And then and then just have a single layer which does that. So yeah, so that's why you don't have linear everywhere here, because it's just a waste, because, you know, so that's why if we have nonlinear, then we really do have a difference here where these variables, these latent variables, are distinguished from each other. They're distinctive. So the hidden variable here will mean something more than the hidden variable here. This won't just be a scaled version of this because of those nonlinear activation functions. They change them kind of fundamentally. So generally, we might have linear activation at the output. We're going to have nonlinear activation in the bulk of the network. Okay, now, a lot of you have probably heard about convolutional neural networks. We're getting there. A convolutional neural network is a type of this, and we'll talk about why we have convolutional neural networks. But for now, we're sticking with this very general version where we're going to refer to this, each layer, as being a fully connected layer. And that just means that this layer is connected to everything from the layer before it. And so we'll say all of these are fully connected layers. In principle, you don't ever build a neural network where every layer is fully connected, and because it's just too hard to train. But we're going to talk about that, and then after we talk about how you, in theory, train these networks, then we're going to then talk about what are special versions of the multi-layer perceptron or the feed-forward neural networks that are easier to train. And that's where we get into things like the convolutional neural network. All right, so any questions before we get into training of this thing and the so-called backpropagation? Oh, I see a question popped up here. All right, so there's some things that are a little bit out of scope that I don't really want to get into here. Somebody asked about the trade-off between bias and variance, and that's just kind of a general machine learning type question or stats question that will apply just as well here to other things. So I'm not going to worry too much about getting into that right now. And there's some questions about gradient ascent, which is about to what we're about to get into. And does multi-layer, given the benefit of training gradients fast? Okay, then there's questions about backpropagation, but we haven't even gotten into back. That's what we're about to discuss. So I'm going to hold off on those questions too. Okay, so then the question is, how do we do, this is multi-layer perceptron supervised learning. So supervised learning means we have ground truth or a training set where we know desired outputs for given inputs. So for now, we're talking about supervised learning, where it's kind of like in the car example. I have a bunch of features, and I know with each one of those features correspond to an American car or an import. And so I just load a bunch of those things in. Here are all of the American cars I know so far, all of the imports I know so far. And then after I train the neural network, it approximates that data set so that later, when a new car is built, I can take those features in without knowing if it's an American car or an import. I don't know why I'd want to do this, but then I could take those features in, plug it in my neural network, and it would make a prediction. Based on past data, this looks like an American car. Based on past data, this looks like an import. And so that's what I mean by supervised learning. It's supervised in that I give you the inputs and outputs, and I'm effectively rewarding you by getting it right. And so we need to see, how do we do this, this process? And this is done with a fancy name called backpropagation, which I kind of hate. So some computer scientist somewhere realized that they could use a gradient climbing algorithm or a gradient descent algorithm to optimize a neural network, and realized it might be hard to do that. So they applied the chain rule a couple of times and figured out that that you could actually optimize all the weights in a neural network with just using their gradients. And it happens to have sort of a pattern where you evaluate things moving backwards through the weights first, and then moving back forwards through the neural network to calculate the next value, and doing that back and forth. And the math behind this is easy. Well, it may seem like a lot of math at first, but it's basically high school level math. It's nothing that complicated. It's named because of sort of the algorithmic process of unrolling these gradients and evaluating this function. So it gets this fancy name called backpropagation. But whenever someone says backpropagation, what they're really just saying is you're applying a gradient descent algorithm to minimize a loss function on these neural networks. So there's it's just a fancy name for using gradients. And so let's see what we mean by that. So like I said, for every input, X, there's a produce output, and I'm just going to say a scalar output Y for now. And so then we have a training set of, let's see what variable I used, of n data points, capital N data points. And so you can imagine we've got like an x1 and a y1. We have an x2 and a y2, all the way up to an xn and a yn. And so we have inputs and outputs, and we would like the weights of this neural network to approximate whatever this relationship is. So we're just doing regression. We're doing nonlinear regression here. And so because our goal is to choose the neural network weights to ensure, I'll say Y estimate, and this is the output of the neural network, is close to Y for given inputs. And so how do we do that? This sounds like an optimization problem where we're minimizing the mistakes that the neural network makes. And so we can come up with a so-called loss function that we want to minimize. And so I'm going to introduce this loss function, which is just the sum of squared error. You can use other loss functions, but it's sure nice if they're differentiable. And so, so that's one of the reasons why this is commonly used. And that loss function is basically going to be E is our loss function. Imagine we're like minimizing energy for E. And I'm just going to take the, I'm going to do 1/2 scaling. It doesn't really matter the 1/2 here, but it just makes the differentiation easier later, times the average of the kind of squared differences from the desired outputs and the correct output. So I will say this E is equal to 1/2n times the sum. And this will go, I think I used I'll use D for data from 1 to n. And this is going to be my estimate for the given input, for input D, I run it through the neural network and I get an output Y hat. And I'm going to compare that to the desired output Y for that input D. And I'm going to take that thing and square it. And this is, remember, there's n data points. And so if it's an excellent neural network, then all of these will be 0. The loss function will be 0. If it's a terrible neural network, then there'll be huge distances here and that loss function will be very high. So I want to choose my weights to make this as small as possible. So already you can imagine, like, we've learned a ton of optimization meta-heuristics that you could apply to this problem. So you could take a genetic algorithm and you could say, I want to minimize E. And I am just going to use all the weights for my neural network as my genome. And I am going to then iterate over a bunch of weights and try to minimize this thing. Or I could use particle swarm optimization, the same sort of thing. And that would be fine. I've mentioned that genetic algorithms without some massaging sometimes don't do so well with just optimizing these weights, whereas maybe particle swarm optimization does a little bit better. But when you look at this, because this loss function looks so simple, it kind of gives you the suggestion that maybe I actually can use gradient information to guide my search. So particle swarm optimization, genetic algorithms, they kind of take random steps, trial and error, and see how well they're doing. But this maybe suggests that I might actually be able to figure out if I'm standing, if there's an uphill or a downhill nearby for the given weights. And so that way maybe that tells me what my next weights should be based on the kind of gradient at the current weights. So that was kind of the inspiration here. So the thought was, well, how would you do a gradient? So we haven't talked specifically about gradient descent, so I'll just mention that here briefly. So gradient descent, this is, and there are stochastic versions of this which add noise, but it's basically if your gradient is available, then you can have an optimization variable or vector here. So these are all of our collection of weights. So this is collection of weights. And this is step in optimization algorithm. And it's just equal to the previous weights plus, I'll do minus, since we're doing descent, minus some alpha, which I'm going to refer to as a learning rate. In other disciplines, it's called a step size, times the gradient with respect to all of these vector, this whole vector of the loss function E. And so this here is a vector gradient. So if you're not familiar, all this means here is that I am going to take, you can think of this here as a vector where I'm going to take the partial derivative of the loss function with respect to the first weight in my waste vector, the partial derivative with respect to the second weight, all the way down to the partial derivative with respect to whatever number of weights that I have. So I'll call this, I don't know, G. So, so basically, I've got slopes for every weight. So I can say, like, for this weight, I'm sitting here and I'm sitting on an uphill slope. And so if I were to get larger in this weight, I am going to tend to increase the loss function. If this is negative, then that would mean if I get larger, I'm going to tend to decrease the loss function. So each one of these things gives you an idea of the step direction that is most likely to increase or decrease the loss function. And so I can put all of those into this collection, this gradient here, and I can scale them because these are all directional information. That's why this is sometimes called a step size or a learning rate. If this step size is large, then we're going over huge regions of the weight space at once. If it's small, then we're taking very small steps and we're being kind of conservative. And so this is the way I can adjust these things. And so if the loss function is relatively well behaved with respect to my weights, then this should allow me to converge on at least a local optimum for the neural network problem. Yeah.
I don't think you're really gradient descent, but I'm not sure for this application of learning rate. They have like the step size can vary.
Sure.
Their duration, does that be applied to this?
You can. So there's a question about can the step size be adaptive? Can it be changing over time? And yeah, sure. So this is the sort of the salient features of gradient descent here. This is like the canonical gradient descent. In more sophisticated gradient descents, you have adaptive step sizes where sometimes they're large, sometimes they're small. You might also introduce noise. So you tend to be stepping in the direction of the gradient, like sort of the steepest descent, but you actually perturb that a little bit, and that gives you a little bit of exploration. There's a bunch of other things that can be applied to here, but they're all built on top of this structure. All right, so any other questions about gradient descent? We're gonna apply this to our neural network weights under the assumption of that we actually can get a loss gradient for every weight in the network easily. And that's really the question, is that if you think about this giant neural network in the hidden layers, the contribution of a weight in some hidden layer in the middle of that network seems like it's really far removed from the loss function. It's going to involve all the other choices we make of weights along the way. And so it seems like it might be kind of ugly to say, to just know, like if I just look at this loss function here, to say, how is this sum going to depend upon some weight in the middle of the network? That looks kind of crazy. Like, can I really calculate that? And it turns out that due to the structure of this feed-forward network, it is actually pretty easy to calculate that. And that's what we're going to get to here in a second. So questions on the general idea here. We've got the loss function gradients with respect to all of the neural network weights. We're going to use a simple algorithm to iterate onto those weights until we converge upon weights that hopefully are effectively train our network to approximate this input-output relationship. That's the way we're solving this. Okay. All right, so that's our question of is, how, maybe I'll put it down here. The question now is how to calculate the partial derivative of a loss function with respect to some weight, which I'll use the notation this, where here I'm saying this is weight on output I in k-1 layer to node j in k layer. Yeah.
So for this whole process, since all of them is like trying to map input output, would you say this is some sort of like advanced like regression?
Right, that's what I was saying. Yeah, this is just neural networks are effectively a very high dimensional nonlinear regression. All right, so this is our question. How the heck do we calculate this? And these are the kind of the notation I'm going to be using here. And I can sort of, I'll write that out a little bit more cleanly here. Now, one thing that I'm going to, for now, even though this is for, I said this is for D data points. So I said we've got all of these data points here. Well, if you look at the loss function, it's just the sum of errors contributed by each data point. And so the gradient for the gradient is going to just be the sum of gradients kind of across this. I guess if I just write it out. So if I think about it, the partial derivative of our loss function with respect to whatever the weight is, and I'm just going to abbreviate it with W right now without the subscripts, is just going to be 1 over n times the sum from d equals 1 to n of the partial derivative of what I'll call ED, which I'll draw here in a second, with respect to that weight, where ED I'm just defining as the difference y d hat minus yd. And so really what we're saying here is, and I think that's what I want, yeah. So really what we're saying here is that the partial derivative, the derivative with respect to the weight, is going to end up being the average of the, so the partial derivative of the total loss function is just going to be average of the partial derivative of the loss functions evaluated for each individual data point. So it's like the first data point contributes a gradient, the second data point contributes a gradient, the third data point contributes a gradient, and so on. And so because it's just this simple sum here, then really the question is, how do I do this per data point? And then I can sum these all up together. So I am going to imagine the process where I only have one training point. I'm really just trying to say, find the weights. I have one input vector and one output. And I'm saying, what are the best weights? How do I calculate the gradient so that I can find the best match for this one data point and this one output? And if we do that for all of our data points and all of our outputs, we can add up all of those gradients together, and that will give us the gradient across for the total function. And that's actually what we use in our gradient descent. So we're just going to focus on, So we focus on a single data point for the following, and then sum later, and then sum or average to get total gradient. So with that, we're just basically imagining that we have an input, which is our X bar, and an output that is Y. So one data point. So find partial E, partial W, and remember this is K, I, J for this case. Hopefully that'll make more sense as we go here. All right, so how do we start this backpropagation process off? Or what I keep calling backpropagation. So recall, for every neuron that is in this giant mess of multi-layer perceptron, we have this mathematical relationship. And you know, I'd feel bad if some of you have already seen all of this before. So I've got my output of the neuron, yjk. So this is, and I'll write this out. This is layer K. And then in layer K, we have output node J. And so that neuron's output is just going to be the output of an activation function, AJK. That's what that A is here. And it takes, in its argument, the weighted sum of the outputs from the layer beforehand. So I can then write this as the sum of, I'm going to use L from L to, I'll do 0. I'm going to move this down a little bit here so that it's not as compressed. And I'm going to have this go up to R to the K minus 1, where this R is going to be the outputs, I'll say number outputs in layer K minus 1. So I look over all the outputs in that K minus 1, and each one of them is going to have a weight associated with them, weight Lj in layer K. And that will be multiplied by the actual output from that previous layer in that layer K minus 1. And so I'll just write this out. This is weight applied to output L from layer K minus 1. Yeah, and then it's used, so, and that's the weight applied to output L from layer K minus 1, which then gets accumulated on our node J in this current layer K. And then this O is the actual output from layer K minus 1 node L. All right, so it's a lot of variables, a lot of subscripts, a lot of superscripts, but it is just this is trying to capture every single neuron in the entire feed forward network. So you can also view this YJK, if you prefer, as OJK. I just made it Y because we called the output of the whole network Y, and we're going to start with Y. But we can also call it O is fine as well. All right, so any questions about this so far? Is this pretty clear that this is the output, or this is a description of all the neurons that we've got? All right, so to make things a little cleaner, I'm going to introduce something that takes the place of this argument. And I'm going to say let x jk be defined as, well, triangle equals, defined as that sum. Rk minus 1, W, Lj, K, O, Lk minus 1. All right, and that's just to clean up this a little bit so that so later we can start using x instead of this giant sum, and we can take partials of x with respect to the weights as well. Okay, so let's try to get the main step here. So this is something we need to remember. So what I'm going to say is, so now I need to, the whole goal is to find this partials. And so I'm going to say, well, the partial of our loss function with respect to any of these weights well, we can apply the chain rule. And so we're going to break this up a little bit. We're going to say, well, that's just the partial of the loss function with respect to this, the variable stand-in for the activation function times the partial for the activation function times that x, or of that x that I just introduced. And then that finally is going to be that x times the partial with respect to our weight. And that's just the chain rule. Is that pretty clear? That's going to drive this whole thing. All of backpropagation is the chain rule. All right, so now we have really two cases to think about, and I think I have a couple of minutes, so let me at least kind of show you where this is going. We really are going to focus here on what happens if we're in the output layer or the hidden layers to this term right here. So if you're in the output layer, I'll do this maybe. So if you're an output layer, so if I'm in the output layer, then the partial derivative of the loss function with respect to this kind of this output function is just going to be equal to the error. So it's going to be equal to the output at the output layer minus the desired output. So this is basically just the error. Otherwise, if you're in a hidden layer, then it's just going to be equal to the partial derivative of E with respect to this guy is going to be equal to the sum from L equals 1 to the number of units in Rk plus 1 of the partial derivative of E with respect to AK plus 1 times the partial derivative of a k plus 1L to the actual AJ that we care about. And this is just the total derivative. And this thing here is just the weight JL k plus 1. And I'll go over this again next time, but I just wanted to at least put basically the punchline here. And then again, we'll go over this in a little more slowly before. What this basically says is that I can take the error function in, and with the error for my particular point, I can calculate this thing, and these will end up being calculable as well. And that will allow me to calculate gradients in the output layer. And then those gradients will actually then be passed down to the layers before them. So what this is saying here is the gradients at earlier layers are functions of gradients at later layers. So I have the ability to set the gradient at the output layer and then pass the gradients down to the earlier layers. And that's what's happening here. So this is a later layer, this is a downstream layer, this is an upstream layer, and I'm passing the gradients from the downstream layer to the upstream layer. And so there, I can in one pass go backwards through the whole multi-layer perceptron and calculate the gradients across the whole network, and then go forward and calculate the outputs to calculate a new error, and then do that back and forth and back and forth. And that's backpropagation. So I just summarized that a little faster than I wanted to. So we will do this again. We'll see this again on Tuesday. I think this weekend there's some things due. I made some extensions. Let's take a look at the Canvas announcements for those extensions. I don't want to misquote myself. Don't forget about the muddiest point. But if this is a little confusing, I'll pick up right here next time with and sort of point out exactly what all these things are, so that this all makes sense to everybody. So that's all I got for you today. Have a nice weekend. Happy to take questions after class here. Before I end the call, are there any questions online? If not, I will see everybody next week. Okay.